Namaste. My name is Bhaskar Kamble. In this presentation, I would like to talk about an astronomical formula given by Bhaskara I in the 7th century in the Laghubhaskariya. So Bhaskara I, I will talk about him in the course of the presentation. And before I begin, I would like to mention that my book on the history of Hindu mathematics is available from Garuda, and here is the link for buying it. And in this book, I talk about the historical and philosophical aspects of Hindu mathematics and the tremendous impact it has had on the rest of the world. And I also discuss about the reasons why this has not become part of mainstream history of mathematics. So this book has been reviewed and read and reviewed by many prominent academics, scholars, and writers. So yeah, so you can get it from this link here. Um, Okay, so the astronomical formula given by Bhaskara I is contained in this Sanskrit shloka here. Saptarandhragni rupani paramapakramo gunaha tat sfutarka bhujabhyasas trijya yeshtapamo hritah. So this is given in chapter number 2, verse 16 of the Laghubhaskariya. So literally the verse translates as follows. 1397 is the R sign of the greatest declination of the sun. That multiplied with the R sign of the true longitude of the sun and divided by the radius is the desired R sign of the sun's declination. So, in this translation, there are certain conventions used in Hindu astronomy and trigonometry, which have to be kept in mind to understand this verse, and which we will look into in the as we go along. But here it just suffices to say that this translation in modern mathematical notation would be expressed as this formula: sine delta is equal to sine epsilon times sine lambda. So delta in this case is the declination of the sun, epsilon is the obliquity of the ecliptic, and lambda is the longitude. I mean, delta, lambda, they are both parts of celestial coordinate systems, which we will look into later. A few words on Bhaskara I. He was a prominent Hindu astronomer and mathematician whose works were extremely influential in the development of mathematics and astronomy. So he was from the 7th century CE, and his works went on to play an important role in the development of astronomy in the Arabic world and subsequently in Europe. And his major works are the Laghubhaskariya, the Mahabhaskariya, and he has written commentaries on Aryabhata's works. He was a devotee of Lord Shiva, and he was also contemporary to the famous Hindu mathematician Brahmagupta. So, okay. And I would like to mention that in the discussion of astronomical concepts, especially the celestial sphere and so on, it's very important to have a good understanding of, to be able to visualize 3D objects, especially when it comes to the celestial sphere. So for that purpose, I have made use of several 3D animations, 3D graphics and animations in this video, which I have done with the help of the R software, especially the RGL package. So more information on that in these links provided. Okay, so I'll begin with an introduction to spherical triangles, what they are. Then I will introduce the so-called cosine formula for spherical triangles, which is an important relation in spherical trigonometry. Then I will go on to discuss an application of the cosine formula to the celestial sphere. And finally, I will discuss. Finally, we will go on to the formula given by Bhaskara I, which we saw at the beginning of the presentation for the declination of the sun. So, and I will also give the Sanskrit text and how it translates to the English. So here goes. So let's begin with spherical triangles. What are they? So okay, so here I start with the first graphic. So spherical triangles are simply um, triangles on the surface of a sphere, very simply spoken. But there are some points which we have to keep in mind. So you take a sphere and you make any 3 points on the surface of the sphere, in this case A, B, and C, and you consider the points A and B, and you make a plane passing through A, B, and the center of the sphere. So you get here in this case this plane. So since this goes also through the center of the sphere, the circle of intersection is the so-called great circle, which divides the sphere into two equal parts, something like the equator of the Earth or any one of the longitudes. So you can see here, if I move this, it divides this into two equal parts, passing through the center of the sphere also. So this arc AB would then be the first great circle, would be the side of the spherical triangle. This would be one of the first side of the spherical triangle. Then you do the same with points B and C, and you get this plane passing to the points B and C, and this is also another great circle here, this one, and you get the points, you get the side BC of the spherical triangle, and so that's how you get two of the sides, and finally you do the same thing with points A and C, and there we go. So you get the all the three sides A, B, B, C, C, A of the spherical triangle. So all of these arcs lie on great circles through the sphere. So like this. Okay. So this is an example of a spherical triangle. Now, just like triangles in the plane, two-dimensional planar triangles, they have also three. They have three sides and three angles. In the same way, spherical triangles also have three sides and three angles. So these are the three sides, and then these are the three angles: this angle, and this angle. So angle A, angle B, angle C, and the sides BC, which is denoted by the small letter A, then the side AC, which is denoted by the letter small b, and AB denoted by the letter small c. So these are the three sides. Now there is an important difference when we speak about sides of a spherical triangle. Sides in a planar 2D triangle are usually lengths, how long each side is. But in this case, this side, for example, is not the length of this arc, but it's rather the angle subtended by the arc BC at the center of the sphere. So it is angle BOC, which is the arc, which is the side BC, or small a in our notation. So, and similarly, this side AC is a angle AOC, and this side AB is angle AOB. So, and then um, and then to define the angles capital A, capital B, capital C, you need to look at as follows. So, for example, the angle capital A is given by first making a tangent through the point A to the arc AC, and the tangent to the arc AB through the point A again. And it's the angle between these two tangents which is the angle capital A. And you can see that this angle is also the same as the angle between these two planes, AOC and AOB. So this we can also see by moving this so that A lies on top of the center of the sphere, and the angle between the tangents is the same as the angle between these corresponding planes. Now, so now that we know what the sides and angles of a spherical triangle are, we are now ready to look at one of the most important relations in spherical trigonometry. Yeah, this is just a repetition of what we just saw, the construction of a spherical triangle. So, okay. So, and that relation is the so-called cosine formula for spherical triangles. And that is given by this formula. So, cosine A, small a, as mentioned, it is this side arc BC, angle BOC. Cosine A is equal to cosine B, cosine C, plus sine B, sine C times cosine of A. So this is the relation which we will be using in this presentation, and I will not be giving a proof of this. The proof of this is pretty simple to understand, and here I've given an example from this reference here, so you feel free to check this out if you are interested. But for the rest of this presentation, it's not important to know the proof. So, okay, so now we will go on to the celestial sphere and apply the formula we have just seen, the cosine formula, to a spherical triangle on the celestial sphere. So in case you are not familiar with what a celestial sphere is, I have made a video of this, and I've given the link to it in the description. You can check it out. Okay, so a celestial, I'll just give a very short description of a celestial sphere. It's a sphere of arbitrary radius with the Earth at the center, and and all the objects are supposed to lie on the surface of the sphere, because in this case the distance from the Earth is not important. It's only the position in the sky which plays a role. So all the objects on the celestial sphere have two coordinates, because yeah, because the distance is not important. And And there are certain concepts involved with the celestial sphere. One is the so-called celestial equator, which is in this case shown by this circle. It is a circle which is, so to speak, parallel to the Earth's equator. So so if you extend the equatorial plane of the Earth, if you extend that, then it will intersect the celestial sphere in this great circle. Now, then you have the concept of the so-called celestial poles, north and the south celestial poles. So when you extend the axis of the Earth's rotation, it will intersect the celestial sphere in 2 points. Here is the point P, which is the north celestial pole, and there is the corresponding point south celestial pole on the other side. And then you have this circle, which here is the ecliptic circle. So the ecliptic circle is the ecliptic plane in this case. So the ecliptic plane is the plane in which the Earth revolves around the sun. So and if you draw a perpendicular to the ecliptic plane passing through the Earth, it will intersect the celestial sphere at a point known as the ecliptic pole, and which we denote by the letter K. So if the center of the sphere or the location of the Earth is O, then OK is perpendicular to the ecliptic plane, and OP is perpendicular to the celestial equatorial plane. So, and another thing is that this point gamma is the intersection of the ecliptic circle and the celestial equator. And this point is known as the equinox. So there is one point of intersection here and another point of intersection on the other side. So yeah, so this point is known as the equinox, as mentioned. So now it's interesting to remember that because the Earth rotates about its axis, this axis, all objects with respect to the Earth appear to rotate in circles about the Earth. So I will just show a video of that here, how it looks in this case. So here we are. So this is the ecliptic plane. The ecliptic plane also rotates. Then the P, of course, it remains fixed because it lies on the axis of rotation. The ecliptic pole rotates, and X is any. I forgot to mention here. Maybe I just go back here and mention once again in the presentation. So X is any arbitrary object in the night sky. It can be the sun, it can be the moon, or star, anything, or planet. So this point here is so this object we denote by the letter X. So as mentioned, because of the Earth's rotation, all the objects appear to rotate about the Earth along this axis, and which is what we saw just now in this video. So I'll just show it once more. Yeah. So as you can see, the object X rotates also about the Earth. The ecliptic pole also rotates, and the point of equinox, and all the stars and planets appear to rotate. Here I've shown the constellation Orion. Likewise, all other stars, they appear to rotate about the Earth. So, and they rotate in a circle. So for example, for X, you can see this circle. These circles are known as the diurnal circle. So which relates to the rotation of the Earth. Okay, so now we take these 3 points, P, K, and X, and we construct a spherical triangle on this. So here we go. So, and now we would like to apply the cosine formula to this triangle, and for that we would need to know what the sides of these triangles are and what the angles are. So for that, it's then useful to introduce the basic ideas of celestial coordinate systems, the equatorial system and the ecliptic system. So in the equatorial system of coordinates, any object, in this case X, has the coordinates alpha and delta, known as the right ascension alpha and the declination delta. So so here you can see in this case. So in this case, so what is the declination? What is the right ascension? Well, the declination is the angular distance of the object X from the celestial equator. So in this case, if you make the angle XOQ, this angle XOQ is the declination delta. And well, this arc lies on the great circle or on the sphere. So because this lies on a circle whose center is also the center of the sphere. So this is declination. And what is the right ascension alpha? Well, it is the angle QO gamma. So QO gamma would be the right ascension, which I have not shown here. And in the but if you use the ecliptic system of coordinates, you will have two quantities for the coordinates, that those are known as the latitude and the longitude. So the latitude is given by the angle XOL, so which is the angular separation from the ecliptic circle of the object, and angle LO gamma would be the longitude. Okay, and this is not to be confused with the terrestrial latitude and longitude as we know on the Earth. So these are not related to that. Okay, now one important thing we need to also remember, as has been mentioned earlier, that OP is perpendicular to the equatorial plane, and OK is perpendicular to the ecliptic plane. So that means that angle POQ will be 90 degrees, and angle KOL will also be 90 degrees. Okay, so that means we already now can begin expressing the sides of the spherical triangle in terms of beta and delta. How? Well, angle POQ is 90 degrees and angle XOQ is delta. So angle POX is 90 minus delta. So here angle POX is now this side, which we call small a, is equal to 90 minus delta POX. So this side A is known 90 minus delta. Similarly, um, KOX plus XOL is 90 degrees. So this side C is 90 minus beta. So KOX is 90 minus beta. So we know two sides, A and C. What about this third side? Well, just remember that this is the angular separation between the ecliptic pole and the celestial pole. That is, by how much is the Earth's axis tilted. So that we know is approximately 23.5 degrees, and this angle is known as the obliquity of the ecliptic, which is denoted by the letter epsilon in our presentation. So this side B is an epsilon. So we know the three sides of this spherical triangle. Now we need to know this angle K. So what is this angle K? Well, for that, let us make a tangent through the point K to the arcs KP and KX. That the angle K would be the angle between these two tangents, this line and this line. What is this one? Well, for that, it helps to understand this by observing the fact that this tangent and this tangent, this is the tangent to K gamma. So this is this is 90 degrees, this angle. And why is this 90 degrees? Well, because remember that OP is perpendicular to O gamma, because gamma lies on the equatorial circle. And OK is also perpendicular to O gamma, because gamma lies on the ecliptic circle as also. So because this is the point of intersection. So the only way that both OP and OK can be perpendicular to O gamma is by the fact that uh, the plane PKO and the plane OK gamma, they are perpendicular to each other, which means that this angle is 90 degrees. So we can also see this here. I will just okay, so now we have this 3D graphic. So if I just move this point K so that it lies on top of the center of the sphere, you can see that this plane PKO and the plane OK gamma, visually you can see that they are indeed 90 degrees. So this angle is indeed 90 degrees. Now we need the angle K, which is this one. So since this is 90 degrees, now what is this angle between this one and this one? Well, we had just seen that this is nothing but the um, longitude lambda. So gamma OL, gamma OL, this angle is the longitude lambda, and that is the same as the angle between this line and this line. Okay, so right, so I just bring it here once again, and you can see indeed that the angle between these two planes, this plane and this plane, which is gamma, is the same as the angle between this line and this line. So that means that this angle K is 90 minus lambda. Okay, so that means that we also know the angle K, which is equal to 90 minus lambda. And now we can start applying the cosine formula to this spherical triangle. So the cosine formula is given by this from here, and the side A here, as we saw, was 90 minus delta. So cosine 90 minus delta becomes sine delta. This B, angle B, is KOP or POK, which is 23.5 degrees approximately, epsilon. So which we call epsilon. So cos P is cos epsilon. Then cosine C was KOX. KOX was 90 minus beta. So cosine C becomes sine beta. And the same for the second term, sine B remains sine epsilon, sine C becomes cosine beta, and cosine of A, because capital A is nothing but this angle K here, 90 minus lambda, cosine 90 minus lambda is sine lambda. So this is the formula which we get by the application of the cosine formula to this spherical triangle PKX. So, okay, so till now, we have not made any restriction on where the object X is. It can lie anywhere on the celestial sphere. But now suppose we say that the object X is the sun. So the sun will always lie on the ecliptic circle. That means for the sun, the latitude, the beta for the sun is always 0. So if you say that X is the sun, then that means sine beta, sine 0 will, then the first term will vanish. It will not, it will not be present, and this, in the second term, cosine 0 is 1. So we will be left with the relation sine delta is equal to sine epsilon sine lambda. Here, sine, so, and this is exactly the relation which we had seen at the beginning of the presentation when I had given the translation of Bhaskara I's verse. So now let us see how Bhaskara I has described this in his Sanskrit shloka. We will go back once again to the verse. Saptarandhragni rupani paramapakramo gunaha tatsfutarka bhujabhyasastrijya yishtapamo hritah. So for understanding this shloka, there are certain things we need to keep in mind as regards the conventions used by the Hindu astronomers. The conventions used in trigonometry and in astronomy, and in expressing numbers. So the first point we need to remember is that numbers were expressed in a Sanskrit verse or a shloka by either the Bhuta Sankhya or the Katapayadi system of notation, usually. So, so Aryabhatta had his own system, but we will not go into that right now. So the main ones were Bhuta Sankhya and the Katapayadi system of notation. So in this verse, the very first word, Sapta Randhragni Rupani, it consists of four words: Sapta, Randhra, Agni, and Rupa. So I have written them down here in this table. Sapta is literally the Sanskrit word for seven. So, so there is no doubt about what this means. The rest of the words, they follow the Bhuta Sankhya system of notation. In this system, numbers are expressed by certain words. So there are so for example, the number one is expressed by certain words, the number two is expressed by certain words, and so on. So in this case, the word Randhra, for example, one of the words for expressing the number 9 is the word Randhra. So the logic behind this is that Randhra in Sanskrit means a hole. So this refers to, and why does this refer to 9? Well, it refers to the human body, the holes, number of holes in the human body. So you have two eyes, two nostrils, one mouth, and two ears. So you have seven, and plus two holes for the excretory organs in the front and the back. So 7 plus 2, that is 9. So Randhra would mean 9, is one of the words used for 9. Agni, well, according to Ayurveda, there are three types of fires or Agni. So Agni refers to three, and Rupa is one of the words used for denoting one. So, so I have discussed the Bhuta Sankhya system of notation in detail in my book. You can feel free to check it out. And I would also like to mention that the famous book by Datta and Singh, Source Book of Hindu Mathematics, they have also described the Bhuta Sankhya system of notation. And here, for example, for each of the numbers 0, 1, 2, 3, they have given a list of words which were used for signifying these numbers. So the number 1, for example, is represented by all these words, and one of the words is Rupa here, you see. So rupa in this case is used for 1. Then for the number 3, one of the words used is agni. So agni is what is used here. And for 9, one of the words used is randhra here, so which is also what is used here. So, so in this shloka, the first word refers to the number 7931. So one important point to remember is that in the Bhuta Sankhya system of notation, the numbers are written backwards. So instead of reading this as 7931, you have to read this as 1397. That is 1397. So, so this first word refers to 1397. Now let us look what the rest of the shloka means. So Saptarandhragni Rupani 1397 is the gunaha. This gunaha, that is the word, it means this is one of the words for R sign. So 1397 is the R sign of the of what? Of the paramapa kramaha, of the greatest declination of the sun. So so for here understanding this part, we need to know one more convention used by the Hindu astronomers in trigonometric convention. So today we use the functions cosine, sine, etc. But the Hindu mathematicians, they used the function r, radius times sine, or radius times cosine. Now, what radius of what? Radius of which circle? Well, they used a trigonometric circle whose circumference was 21,600 units long, and depending on the accuracy of the circumference to diameter ratio, or the or pi, they would use they would use length for the radius of the circle. A very common convention was a very common choice was 3,438 units for the radius of the circle in Hindu astronomy. So with this, the value of pi turns out to be as given here. And if they wanted to use more accurate values of pi, then they would adjust this radius accordingly. But this was a pretty common convention to use 3,438, and Bhaskara I has also made use of this in his works. So, so according to this translation, 1397 is the R sign of the greatest declination of the sun. So the greatest declination of the sun is also equal to the obliquity of the ecliptic. The declination of the sun can never exceed that. So let us check if this is indeed the case. Since the radius is 3438, R sine epsilon is 1397. And if you then replace R by 3438 and divide 1397 by this radius 3438, you will get sine epsilon equal to 0.40634. And now from this, you can get the angle epsilon by taking the inverse sine function, and that is then equal to, if you do that, you get epsilon is approximately equal to 23.97 degrees. And that is uh, the obliquity of the ecliptic. Yeah, I mean today we it is approximately 23.5, but in these works it is taken to be as about more closer to 24. So this is what we have seen, how we can make sense of this first part of the verse, that 1397 is the R sign of the greatest declination of the sun, or the obliquity of the ecliptic. So so that is R sine epsilon multiplied with the Sphutarka bhuja. This is the R sine of the longitude of the sun. So R sine epsilon multiplied by R sine longitude, R sine lambda, divided by the radius. So R sine epsilon times R sine lambda divided by R is nothing but R sine epsilon sine lambda, is equal to the desired R sine of the sun's declination. So Ishta is desired, and Apama is R sine of the sun's declination. So R sine of delta. So this means nothing but the fact that R sine delta here is equal to R sine epsilon sine lambda. So, and this is how this Sanskrit verse can be understood in today's terminology to stand for this formula. I would also just yeah, the word hritaha means divided. One of the words for divided. Abhyasa is it means to multiply. Here is the word abhyasa, and then yeah, trigyaya is the radius. So the word trigyaya in Sanskrit, in Hindu trigonometry or astronomy, stands for the radius. So why is it? It's an interesting point to understand why trigyaya means the radius. So Jya is Trijya, actually Trijya. So Jya is the Sanskrit word for the sine function or the r sine function, the r sine function. Okay, so Jya is the r sine function, and Tri means three. Three what? Well, three in the case of in this context, it means three zodiacal signs, zodiac constellations. So there are 12 zodiac constellations on the ecliptic. So and 360 degrees in a circle. So each constellation is then 360 divided by 12. That is approximately 30 degrees. That's actually equal to 30 degrees. 360 divided by 12 is of course 30. And so one constellation can be said to take 30 degrees, and three constellations would take 90 degrees. 30 times 3 and 90 degrees. So the sine of this, so the r sine of this, so r sine of 90 is r times 1, so that is equal to r. So that's how the word trijya means radius in Hindu astronomy. So okay, so this is how we are to understand this verse to get this formula. And here is the translation once again, um, from K.S. Shukla's edition. And the same verse is also given in the Mahabhaskariya, chapter 3, verses 6 and 7. And I would like to mention at this point that uh, the the astronomical knowledge in the Hindu astronomical works and mathematical works were very much in demand in the Arabic world and in the European world, because of two reasons. Because in those days, for navigation on the seas, you needed to have a good knowledge of astronomy to be able to tell the directions from the sun, from the stars, which direction you are going. This was extremely important. And the Bhaskara's works have, these results, as we just saw, and many other results which I may try to do at some point, cover at some point later. And the other reason was that uh, astronomy is extremely important also for a good calendar. And Europe was in the need of a good calendar. And we know this from the Gregorian reform of the calendar of the late 16th century. And in fact, there were many Jesuit priests who had been trained in mathematics and sent to India by Christophe Clavius for getting the mathematical knowledge of India. So all these things I have discussed in detail in my book, the historical aspects of these things and the transmission in this book. And yeah, and here are the references which I've used mainly in making this presentation. There is a lot more interesting and rich information and knowledge available in these works. So feel free to check it out, and thank you for listening.